Good afternoon, my name is Clarissa Spertino. I am a student of Information Systems Engineering, and since last year I am participating on an investigation project with Maria Julia Blas and Silvio Bonet. In the context of this investigation project, we did the paper Developing RDEVS Simulation Models from Textual Specifications that I am going to present now. First of all, I am going to introduce some concepts that I consider are important to understand the rest of the presentation. When we talk about a routing process, we mean a system of interacting components in which the operation of an element and the routing of its outputs depend on what's happening throughout the process. These routing processes exhibit a strong interdependence between their components, and that's why the network theory is useful to model their structure. The network theory proposes to model a system as a set of nodes connected by links. The nodes represent the components, and the links represent the interaction between these components. So we can say that a routing process can be seen as a constrained instance of a network model. The RDEVS formalism is based on DEVS. It's a new formalism that emerged from the modeling and simulation community to address new type of problems. The RDEVS simulation models can be executed using DEVS simulators. This formalism proposes three types of models: essential model, routing model, and network model. Each one belongs to a modeling level and plays a role in the routing process specification. The essential model defines a DEVS atomic model that specifies a domain behavior. The routing model defines a container for an essential model that uses a routing policy to manage its input and outputs. And the network model defines a set of routing models coupled all to leave the routing functionality to the routing policies. So the essential model describes the internal operation of a component. The routing model represents a component included in a routing process, and the network model structures a routing process as a composition of routing models. So the RDEVS simulation models provide a formalization of routing processes through three modeling levels that I showed before. Although RDEVS is a subclass of DEVS, due to the modeling distinction between DEVS and RDEVS, new modeling strategies are needed to support the development of RDEVS models. So the goals of our paper are to provide a transformation process between constrained network models and RDEVS simulation models using Eclipse technology, and to add such a transformation process as a new feature of a modeling and simulation software tool for the execution of RDEVS models in DEVS simulators as discrete event simulation models. Now I'm going to talk about defining routing processes using constrained network models. By using abstraction models to define routing processes, we present a textual representation based on network theory. The textual representation that we call RDEVS natural language is supported by a context-free grammar, also called RDEVS natural language, that is based on a constrained network model to approach the definition of routing processes through the RDEVS formalism. This grammar abstracts the definition of routing processes into textual representations using nodes and links to describe their structure. There are two versions of the grammar, one in English and the other in Spanish. Both of them were developed using ANTLER. In the English version, we can find three primary building blocks: network, materialize, and edge. When a RDEVS natural language specification is used to structure a routing process, a network is defined to model that process. So the first building block, network, is used to define the routing process and the nodes that are part of it. In a routing process, each component exhibits an internal operation and defines the behavior of a node or a list of nodes. So the block materialize is used to establish the behavior that each node will execute. And then links define directed interactions between the nodes. So with the sentences from the edge block, we can define these directed interactions between the nodes. There is an Ecor metamodel that was developed using EMF. This metamodel is used to validate the routing process definition from a constrained network model specification. The stereotypes are used in the metamodel to indicate the network model component to which the routing element refers. We can see in the metamodel that a RDEVS natural language specification includes a routing process. This routing process is related with the concept of a network model, and it has a name to identify it. The routing process is defined over a set of components, where each component executes the behavior of a component type. Both component type and component are identified by a name. The routing process includes a set of interactions. Two components are linked in an interaction, where one of them acts as the source from where the interaction takes place, and the other as the destination, to where the interaction is directed. This metamodel is restricted with object constraint language constraints to ensure obtaining a routing process from a network model definition, and this is what we call the constrained network model. These constraints guarantee the integrity of the metamodel as follows. At least one node must be identified as initial, and at least one node must be identified as final. Nodes cannot be isolated. Multiple links cannot connect the same pair of nodes. A component must execute a single behavior. Self-links aren't allowed. And a single routing process must be described in a RDEVS natural language specification. In our proposal, we implemented a plugin for Eclipse platform that is called RDEVS Natural Language Editor, and it is composed of a text editor, a wizard, and a validation process. The text editor allows specifying valid constrained network models using the RDEVS natural language syntax. It offers some written aids to help the modeler during the edition of the textual specification. Also, the wizard is useful to create files with a particular extension. These files are the ones that will store the textual descriptions. And the validation process is used to instantiate the metamodel following the parsing of the textual specification. Now I'm going to show an example to clarify our proposal and to show how to use the software tool. This example is based on a routing process that is composed of 5 machines, from machine 1 to machine 5. And we can see that each machine has an icon related. This icon represents the type of machine that each one is. First of all, the modeler had to create the specification file using the wizard that the plugin offers. The modeler at this point can set a name to the file and also choose the language he will use to work with. If no language is selected, it will be English by default, and the value of the language selected is saved with the file. So when it's necessary, we can read the language that is selected. For example, when the modeler reopens the file or before running the validation process to know which version of the grammar used to validate. Now the modeler can start writing the textual specification. In this case, it started by using sentences from network block to define the network and the nodes that are part of it. In this case, we have 5 nodes from machine 1 to machine 5. Then the second step in this case is the definition of the behaviors that each node will execute by using sentences from materialized block. And at this point, we can see the written aids that the editor offers, such as syntax highlighting and the typing suggestions. These sentences from materialized block allows to associate each node with a behavior of a component. So we can say that machine 2 and 3 are related to the behavior of machine type A, and the rest of the machines are related to machine type B. Now we have to define the interactions between these nodes by using sentences from edge block. We have to say that machine 1 is connected with machine 2 and 3, and then that machine 2 is connected to machine 4, and machine 3 is connected with machine 5. Now we can see that the modeler has a variety of structure to choose from the grammar. So there are different ways to write the same things. When the specification is over, the modeler can start the validation process. In this case, we expect to see a successful message that ensures the textual definition of the network model is in correspondence with a valid routing process. When this happens, we can see that an instance of the metamodel is created. And if we see more details about this instance, we can see that this has 4 interactions, 5 components, and 2 component types. All of them are in a routing process. If we see more details about the component machine 1, we can see that this has a behavior that is related to the component type machine type B. Also, it has a name that is machine 1, and it has 2 interactions. One of them is directed to machine 2, and the other is directed to machine 3. Both of these interactions begin in machine 1. This was a successful situation. When the validation process was activated, what internally the software tool did was navigate the specification to recognize the structure that were used from the grammar. If this structure were used in a valid way, then there is an instance of the metamodel that is created, as we have seen just before, and there is a validation that runs over the instance of the metamodel that was obtained to validate the multiplicities, the relationships, and the constraints that the metamodel included. So in the situation we have seen just before, it was everything okay. But if we introduce a mistake just to see what happens, for example, deleting the letter S to the word connections, we are going to see an error message, and in the view problems of Eclipse, we can see a list of the errors that were found. Also, there is other situation that can cause a mistake, and is, for example, create a connection that is from machine 2 to machine 2. What we are doing is creating a self-interaction in machine 2, and also we are leaving machine 4 isolated. And if we remember the constraints that the metamodel included, none of these situations were allowed. So if we run again the validation process, we expect to see an error message and also the list of the problems in view problems. So if we see more details about one of the errors found, you can see that what caused the error was the violation of the not isolated constraint. In these cases, the modeler has the opportunity to correct the specification and run again the validation process. Now I'm going to talk about from textual specifications to Java classes. The routed devs library extends devs Java to provide a solution for implementing routed devs simulation models in Java and then executing these models using the devs Java engine. In the UML class diagram, we can see that there is a Java class for each type of routed devs model that I presented at the beginning of the presentation. So we can see that the network model class supports the structure definition. Then the routing model class supports the routing behavior level by the set of operations defined in this class, and the essential model supports the domain behavior. If we continue the example I showed before, we're going to see the model-to-code transformation. Using Aceleo, that is a template-based technology that allows the creation of code generators from any data source available in EMF format, what we do is navigate the elements defined in the abstraction model, that is the instance of the metamodel obtained, to write the corresponding Java classes. So here we can see all the classes that were generated after the validation process. If we analyze it in more detail, we can see that there are two classes that extend essential model, one for each component type, that is machine type A and machine type B. The names of each component type are used to name the new classes. Also, there is a class for the routing process defined in the specification. This class extends network model. And also there is an extension of a routing model class for each machine that was for each node in the specification. In this case, also the name of each node is used to name the new classes that are generated. So the main advantages of our proposals are the reduction of implementation times through fast modeling solutions and the simulation model correctness regarding the formalism through well-defined simulation models. Talking about conclusions and future work, we have presented a plugin in development intended to obtain Java implementations of RDEVS models from an abstract model defined in a textual specification. For the textual representation, we propose a context-free grammar called RDEVS Natural Language that is based on a constrained network model. This grammar was implemented using Antler. Also, there is a meta model that is used to map the textual representation with valid routing processes. This meta model allows a direct mapping between its concepts and the RDEVS simulation models. The Java classes are created using Aceleo, and the RDEVS library is used as support, since it enhances the development of RDEVS models in Java using some features provided by DEVS Java. With our proposal, it is guaranteed that the specified model and the implemented one will represent the same after the perform of the transformations that I have named. So future work is devoted to the development of new representations for large-scale routing processes and the integration with graphical specifications that are already defined. The proposal is a part of a work in progress intended to develop modeling and simulation software tools for RDEVS formalism using well-known abstractions to get the computational models through conceptual mapping. Our final aim is to provide a tool that allows the modelers to define the problem using well-known abstractions and also get the computational models attached to such abstraction models through conceptual mapping. Then the modeler, by using the software tool we propose, is abstracted from the notions of the RDEVS formalism and can generate an abstract network model to represent a problem. So the modeler will be able to have simulation models without needing to codify any routing implementation, without having any programming skills, and also abstracting him from the complexity that is always included when using mathematical formalism such as RDEVS. That's all. Thanks for your attention.